Okay, hi everyone. So this work is with Dustin Jamner, Jeremy Seek, and Phil Wadler. And I'm sure you all know Jeremy Seek and Phil Wadler, but I just wanted to point out that Dustin is a very brilliant undergraduate at Northeastern. And he did all of this work during his sophomore year as an undergrad. So I just wanted to point that out. And he did most of the heavy lifting on the paper. Okay, so let me tell you what the paper's about. So you're in the gradual typing session, so we want to combine static typing with dynamic typing. In particular, the feature that we're interested in mixing with dynamic typing is polymorphism. So if you take system S, which has universal types and satisfies parametricity, and you then throw in a dynamic type and you instrument a gradually typed language which allows casts from more precisely typed to less precisely typed code and vice versa, then we would like to be able to prove that we still have parametricity in this mixed language, in this gradually typed language. Okay, so let's talk about parametricity a little bit. So throughout the talk, whenever I write lambda f, that's just my short form for system f, the polymorphic statically typed, no dynamic types language. So in system f, a consequence of parametricity is that we get nice free theorems like this one, which I'm sure you've seen way too many times, that if you have a term e that has type for all x, x to x, then if you apply that to a type A and a value of type A, if you're in a terminating language, you'll always get back the same value, right? That E will always behave like an identity function. If you're in a non-terminating language, we get slightly weaker free theorems, right, as a consequence of parametricity. So our theorem would then say either you get back the value you fed in or your term will diverge. And I just want to point this out because, as we throw in more effects into the language, our free theorems generally get weaker, which we'll see in a second. Okay, so what we want to do now is make system F with a dynamic type. And in particular, the goal here is that even if you start off with dynamically typed code, as soon as you cast it to something that has universal type, that code should behave parametrically. So if we take a look at an example, that red lambda xx up there has type star, the type dynamic, and I'm casting it to for all x, x to x, and then I'm applying it to int and for. So if I run this, the identity function is already, of that type. It's going to behave parametrically. Everything is good. So we'll get a 4. But suppose that I now do the same exercise. I take the add1 function, dynamically typed, and I cast it to for all x, x to x. This is going to take its abstract input and add 1 to it. So clearly, it's not going to behave parametrically. So if we run this, what should happen? Well, clearly, what happened in the first case should not happen, right? That 4 shouldn't just flow in. And if we get a 5 out, that would be very bad, right? That would mean that we are not behaving parametrically. So, right, we've cast a dynamically typed value to a universal type, but we want to be able to do better than this. In particular, in this case, we want to be able to raise, the right answer would be to blame that cast and say, well, it's trying to cast something that's not going to behave, that's not parametric to that universal type. Okay, so that's our design goal. That's how we want our calculus to behave. And in particular, then, in that sort of situation, in the calculus that I want to show you later in the talk, we would want free theorems like this: that if E has type for all x, x to x, then either it evaluates to the same value you fed in, it diverges, or it raises blame. Right? So now we have a third condition: errors come into the picture. Okay, so there's a lot of prior, not a lot, but there is prior work on integrating polymorphism with dynamic typing. So myself, Jeremy, and Phil had a paper with Robbie back in 2011 on the polymorphic blame calculus. Only in that setting, we did not prove a parametricity theorem for the calculus that we had. Earlier than that, in 2008, Jacob Matthews and I did a multi-language that mixed system F essentially with a dynamically typed language, Amal and Scheme. And we tried to prove parametricity for that, but we found out later that there was a flaw in our proof. Later on, Lindsay Cooper and I did a proof of this, but we never sent it out. It was never published, so it wasn't peer-reviewed. So this problem of parametricity, do you have parametricity when you mix polymorphism with the dynamic type has remained open all these years. Okay. Oh, and I just wanted to say, yes, the idea of protection using this idea of runtime sealing, which is what all of these, which is the flavor of protection that all of this work seems to use, really goes back a long, long time, back to Morris from '73. Okay, So what did we do in this paper? We present a polymorphic blame calculus that is a variant of our POPL 2011 paper. It fixes certain topsy-turvy problems of that system, and I'll leave it to you to read the paper to see what exactly that means. I'll just present our calculus today. And then we prove parametricity for this language, which we call lambda B, polymorphic blame calculus. And in particular, what ends up happening is we have to use a step-indexed Kripke logical relation in order to do the proof of parametricity. And that makes sense intuitively if you think about it for a second. We're using a form of runtime type generation in order to dynamically protect our things that should remain opaque. And therefore, this becomes a stateful language, even though you didn't start out with 2 stateful languages or anything like that. Okay, we show that the logical relation is sound with respect to contextual equivalence, and we then use the logical relation to prove a couple of interesting free theorems, which I'll say a little bit more about at the end. Okay, so I'm going to start off with a very quick look at the blame calculus. No polymorphism yet, just so you know the basics. So let's pretend that we're starting out with simply type lambda calculus, and we're going to add in a dynamic type. So those are my types. Int, bool, functions, and star. And we're going to add cast to our simply type lambda calculus. So the cast from A to B with that label on it, P, basically says it tries to cast some expression of type A into the type B. So it essentially checks if E does in fact have type B, and if it does not, then it raises blame. So we also need to add blame to our language. Now, casts, the typing rule for casts basically says that if you can write down a cast from A to B if A is compatible with B. And this notion of compatibility you'll find over and over again in the gradual typing literature. So compatibility for us is that everything, you can cast everything from star to A and from A to star. And for functions, you have the usual rule. Okay. Now, we're going to have values. So the canonical form for dynamically typed values is essentially a sort of tagged value form, where G tells us, is this value a function, star or star, int or bool, all right? And then we have, in this calculus, we have casts from a function to a function. We sort of suspend them. We don't do anything with them until you give us an argument. So they're going to be of a value form. All right. So let's take a look at some rules. If you try to cast a value from that's G to star, right? That's a dynamic value to a ground type G. If the tags are the same, if the types are the same, then you just get back the underlying value. If you try to cast it to some H that is not equal to the underlying tag G, then you get blame. Okay, and you'll see that I'm blaming Q there, not the label that's sitting on the inner tagged value. Okay, so cast to an incompatible type produce blame. Let's take a look at the application. So that form over there, the value cast from function to function, is a value form. When we apply it to some argument v prime, we simply do the usual thing. The argument is cast, in this case, from A prime to A, and we negate the blame label as is usual, and then we cast the result in the other direction. Okay. So let's take a look at a quick example. I have the identity function here that's being cast to int, and then we're going to apply it to a 5. So we basically take 5, cast it from int to star to feed it into the dynamic code, and then afterwards we're going to cast it back to int. There we're casting something that is an integer back to an integer, so this is going to be fine and it's going to succeed. We're going to get the underlying 5. Okay. Let's add polymorphism. So one decision that we made in this calculus is we decided that type abstractions, the body of a type abstraction can only be a value. And sort of a simple, quick explanation I can give you for this is this means that lambda x blame p is a term, not a value form. Now that is not a valid term because the body of a type abstraction must be a value. And so this nicely helps us ensure that for all xx, the empty type is uninhabited as it should be. Okay. All right. So let's try to just sort of naively add polymorphism and see what happens. So here's the normal reduction rule for type instantiation. Nothing is different. This is the standard thing. When we take a type abstraction and apply it to a type, what we always do is we substitute the type A for X in V, in the body of the type abstraction. Now let's look at an example and try to see what happens if we just use this reduction rule. So here's the add3 function. It's of type for all x, x to int. So that's kind of odd, right? It's a function that's taking in something that is that should be opaque, that's of type x, but then we're adding 3 to it. And to do that, we're taking the input and casting it to star and then to int and then doing the addition. So this is not a parametrically behaved piece of code, right? This, when I run this, this should raise blame. Okay, let's see. If we apply add3 to int and 2, it would be bad if we got 5 out at the end, right? Because that means that we're not sort of raising the alarm about how this function is not behaving parametrically. Okay, so let's see what happens. So we apply add3 to int, but I'm using the reduction rule at the top. So I substitute int for x. I end up substituting int for x right there. So now that x in the original code, I've put in int instead of it. Now I take my function and I feed in 2, and we end up with this state where 2 is being cast from int to star to int, which is just fine. So that's 3 plus 2, and that's 5. So that didn't work. All right, so we need to be a little bit more clever because we wanted to raise blame. All right, so what exactly happened here? Well, stare at all the spots that are sort of red. Basically, when we did the substitution, we forgot about the fact that that input x needed to be polymorphic, that we should not be adding it to the number 3. Okay? That would have been our opportunity to raise blame if when we tried to add something of type int to something of type x. Right? But we forgot that because we just sort of naively substituted the type in for the variable x everywhere, for the type variable x. Okay, so substitution is not a good idea for the type instantiation rule. So what we're going to do instead is use runtime type generation, which I've already alluded to. And here's what we're going to do. Our operational semantics is going to be set up so that we have a type name store sigma. Sigma keeps a mapping from type names, alphas. Think of them as, yeah, they're dynamically generated type names. It maps these alphas, these type names, to the type that someone tried to substitute for some variable. And you'll see what that means in just 1 second. Okay, so I have a type name store sigma, and I'm about to do a type application. So how do we want to proceed? Well, we don't want to substitute b for x. So instead, what we want to do is we want to generate a fresh name alpha, something that's not already in the type name store in sigma. We add this mapping. We say, OK, we've just produced a new type name alpha, and we're going to remember that this needs to be a b, because that's what the type abstraction was being applied to. And now, in the body of the type abstraction, we're not going to substitute b. We're going to substitute alpha. OK? So this lets us remember that that needed to be polymorphic or needed to be opaque. OK, so now this part, so far, this v with alpha for x has type a with alpha for x. Well, assuming that, sorry, the lambda x v has type for all x a. I just realized I didn't put that on the slide. So this here has type a with alpha for x. But we know that from our type instantiation, from the typing rule, we know that we need to get something that is of type a with b for x, because we just applied this thing to a b, right? So we need to go a step further. And what we're going to do is then we're going to use this conversion rule. So conversions in this calculus are going to be of the form a plus alpha or a minus alpha. And conversion basically means either you reveal the type associated with alpha, plus alpha. In this case, my plus alpha is saying all of the places in that type where you had alphas, please stick in b's instead of them, okay, and cast it to a b. So now we have something that is of the right type. And Conceal goes in the other direction. It would take generally something that's of the form a with b for x and turn it into an a with alpha for x. And it all depends on what is it that alpha is mapped to in sigma. You need to look that up. Okay. Just a quick look at conversions. So I said we can do plus reveal and conceal. Plus is reveal, minus is conceal. So we have this before I showed you casts, they were of the form A to B with a P cast, with a P label on the cast. Now you're going to see these conversions phi on them. Okay, and this value form right here, I have a value of type A, but it is concealed. So this is a concealed value, and it's going to be a value form. And we have a reduction rule where you can reveal the type, and what all that does is minus alpha plus alpha, you get the underlying value. Think of it as sealing and unsealing. Sealed value just got unsealed. Okay, there are just another little detail. Just like we had function-to-function casts were values, function-to-function conversions are also values with the usual rule. Okay, so if we come back to our example now, we see that we have managed to fix this because instead of substituting int for x everywhere in the original code, we are substituting alpha. And so that means that here, when we try to cast the argument to an integer, we notice that there's a problem there, and this cast right here will immediately raise blame because alpha is not equal to int. Okay? So alpha now is also one of those tags. Okay. All right, so we need to revisit our compatibility rules. We need to throw in a few more. But really, in a nutshell, all I want to say about this is that when you cast out of a polymorphic type, you essentially instantiate the type variable over there with the type dynamic. And when you cast into polymorphic types, you treat them as values, just like functions. Cast functions are being treated as values. Cast universal types are also being treated as values. Okay, so let me talk very briefly about how all of this design that I've shown you feeds into the design of the logical relation to prove parametricity. So parametricity is always proved using logical relations, and generally it says that if you give me related inputs, I'll give you related outputs. And we have to take that general idea and apply it to this particular polymorphic gradually typed language. And as I've said already, lambda b is a stateful language because runtime type generation has similarities, semantic similarities to doing dynamic allocation of references in an ML-like language. So, for those kinds of languages, we end up needing these cryptological relations which keep track of some state, and here we do as well. Okay, so in a normal system F-like setting, many of you would have seen a logical relation where when we try to relate two type abstractions at the type for all xa, what we have to do is say, pick a type for the left-hand side, B1, pick a type for the right-hand side, B2, pick a relation on values of type B1 and B2, because that's where the user gets to pick whatever relation they want. And then, I should have highlighted first, and then what we do is we say, okay, once we've applied the type abstractions to B1 on one side and B2 on the other side, they should be related at the type A, but now we give ourselves the ability to look up when things are related at the type X by looking in the relation R, as it shows at the bottom, right? Okay, here what do we have to do? Well, here we need more information before we can relate values. So this is a cryptological relation, which means that there is some state that we need to keep. We keep that state in a world, W. So you should read this as V1 and V2 are values of type A, roughly, that are related in the world W. And the W keeps track of information about state, what type names exist right now, what are the relations that I should use to look up when values are related to the same type name, and so on. So worlds keep, worlds actually also keep track of a step index and so on. And then right here, that kappa there says, what relation do I use for a type name alpha? I forgot to say, generally in the logical relation I showed you on the previous slide, that row would map a type variable x to two types, B1, B2, and the relation R. But notice that we're not doing that anymore. There's this level of indirection. We're just storing the type name, and then we can go look up the type name in the world and find the relation there. Okay? All right. So I'm going to mostly kind of rush over that. So we're doing something very similar to what I was before. We're picking B1, B2, and a relation R, but now we're sticking them in the world. And I won't go through the definition. Okay. So there's lots more in the paper. There are all of the proofs for parametricity and these two free theorems that we proved, which have to do with the K combinator and sort of these rearrangements with map and polymorphic functions are in the tech report. And we've proved that our logical relation is sound with respect to contextual equivalence, so you can use it to reason about equivalence in the language. That's about it. So what I want to say is that, you know, this settles sort of long-standing open problem. And now you can actually get your theorems really for free, just starting with dynamically typed code. Thanks.